2 liters, 2 liters, 3 liters. Because it only works for gases. And we have solid, so this is not going to work. And in fact, we're starting off with 5.74 grams of KClO3. So if we have 5.74 grams of KClO3, then we're going to go from grams of KClO3 to moles of KClO3. And so we aren't starting off with a volume of gas A. We're starting off with grams of KClO3 solid, pure. And that takes us to moles of KClO3. From moles of KClO3, we'll go to moles of O2. From moles of O2, we have 2 choices. We want to get the volume of O2 gas. To get the volume of O2 gas, A, we could use the molar volume, or B, we could use the ideal gas law, PV equals nRT. We'll do both methods here. And so, in an effort to save time, I'm just going to look up potassium chlorate's molar mass. Its molecular weight is 122.54. So we'll set this up, 5.74 grams of KClO3, and then convert it to moles. 1 mole of KClO3 weighs 122.55 grams. So the grams of KClO3 cancel, that leaves us with moles of KClO3. Then we'll do a mole-to-mole conversion. So 3 moles of O2 for every 2 moles of KClO3. So moles of KClO3 cancel, it gives us moles of O2. Now here we have a choice. Choice A, we use the molar volume. Now, what we're going to do is we're going to do this at room temp and pressure. Room temperature and pressure. What is room temperature and pressure? Well, it's 298 Kelvin and 1 atmosphere. Just do it that way. And what does it come out to? It comes out to 24.5 liters per mole of gas. This is at room temperature and room pressure, RT and RP. If I change the pressure to bar, it would be 24.8. Or I can calculate it, right? But you know, this number is pretty useful. That's A. That gives me liters of oxygen. Or with B, I stop here. Stop here. And so B, I'm left with moles of O2. And so from moles of O2, then I can figure out the volume. The volume of O2 is equal to the moles of O2 times RT over P. And so I could either use the ideal gas law as an algebraic calculation here, or I could use the molar volume. I can calculate the molar volume at any temperature and pressure, you know, so if I'm doing this at elevated temperature, I can calculate the molar volume there. But if I'm dealing with room temperature and room pressure, it's nice just to do it by A. It's quicker. But if I do it at some other temperature and pressure that I don't know the molar volume of, and I have to calculate it, then either way, probably okay. It depends on how many calcs you have to do. All right, so let's see what it comes out to here. I'm just going to use this one. Top one. Well, we could do it both ways. Let's see what it comes out to. 5.74 divided by 122.55 times 3 divided by 2 times 24.5 liters of gas per mole of gas. I'll get 1.721 liters. 1.721 liters of O2. That's if I do A. Well, let's try it with B. If I do it with B, I go 5.74 divided by 122.55 times 3 divided by 2 0.0. So the moles, if I stop here, then I'm going to get the moles, this is going to be 0.07025 moles. And then R is 0.08206 liters atmosphere per mole Kelvin. And then T is 298 Kelvin. And then P is going to be 1 atmosphere. So atmospheres cancel, Kelvins cancel, moles cancel, that just leaves me with liters. So this is going to be times 0.08205 times 298. I get 1.717 liters. So close, 1.721, 1.71. It's close. Their answer is going to be different because their answer is actually going to be smaller. Why is their answer going to be smaller? Their answer is going to be smaller because colder temperature. But they're using bars here. Because that's the one for bars. The one for atmospheres is 22.4. Okay, let's try 31 next. Let's do the chlorine. Let's do the chlorine measured at. Let's do 9.81 liters of chlorine. 9.81 liters of chlorine measured at 298 Kelvin and 1 bar. Now, if you ever forget what the molar volume is, it's simple to calculate. So let's go ahead and, let's say I forgot what the molar volume is at 1 bar. So I forgot that, but I remember what the molar volume is. The molar volume is equal to the volume over moles. That's going to be the volume. Moles, N is equal to PV over RT. We'll substitute that in here, PV over RT for N. So this comes out to RT over P. And so we're going to do this in bars, 0.08206 liters times atmosphere per mole Kelvin. And then we have the T, which is just 298 Kelvin. Actually, let me go more sig figs, 298.15 Kelvin. And then P is 1 atmosphere. This is going to be exactly 1 atmosphere. So let's say infinite sig figs there. So I want this in bar instead. Oops. I want this in 1 bar, so I can't use 1 ATM. I'm going to use 1 bar. Now 1 bar is not the same as 1 ATM. 1 bar is a little bit smaller than 1 ATM. Not much. It's like 1% smaller. Just a tiny bit smaller. But we've got to factor that in. So rather than using 1 ATM, I'll use 1 bar because that's the pressure I want, and then convert it. And so it turns out 1 ATM is equivalent to 1.01325 bar. So we need a little bit more than 1 bar to fit into an atmosphere. Therefore, the molar volume is going to be a little bigger because the pressure is a little bit lower. So let's calculate it here. I gave you the number, didn't calculate it, but let's calculate it. 0.08206 times 298.15 times 1.01325, 24.79. liters per mole. Now, it depends on what class you're doing. You know, in Chem 1A, I would have it memorized. Like, for example, the molar volume. In Chem 1A, I would do it like this. Room temperature and room pressure in atmospheres, 1 atm. It's going to be 24.45 liters per mole. And then room temperature and room pressure in 1 bar, it's going to be 24.79 liters per mole. But since this is Chem 4, we're going to round this. We're going to round this to 24.5 liters per mole, and then we'll round this one to 24.8 liters per mole. Although we should probably leave it at 4 sig figs rather than 3. We're allowed more, actually. Yeah, no, 4 sig figs. All right, and so I'm doing this particular equation for the generation of chlorine. So 2 potassium permanganate plus 16 HCl yields 2 manganese, 2 chlorides, plus 5 chlorine, plus 8 H2O. This is wrong. H2O aqueous doesn't make sense because it's water dissolved in water. Well, water dissolved in water is called liquid water. That is liquid, and then the 2 KCl's are aqueous. Now the chlorine they have as aqueous. Chlorine can be aqueous or gas. Depends on how much you generate. So this is what we're going to do. We're going to do it like this. We're going to go from 9.81 liters of chlorine gas to straight to moles. We can go straight from liters to moles because we know the molar volume. Now, the molar volume in terms of bar is going to be here. And so for every mole of gas, we have 24.8 liters. So for every mole of gas, we have 24.8 liters. So we don't even have a mole of gas here. We have less than half a mole. That's about 10 liters. We need about 25 liters for a mole. And so we'll go straight from liters of gas to moles of gas. This will be moles of chlorine. Then we're going to go from moles of chlorine to moles of KMnO4. And then we want to go to grams of KMnO4. So in this case, we'll use the molar volume. It's going to be 9.81 liters of chlorine. This is pure chlorine gas. And then we know the conditions are such that we get 24.8 liters for every mole. So 1 mole of gas, any gas, is 24.8 liters under these conditions. So that gives us moles of chlorine. And then the mole ratio is a 2 to 5 mole ratio. 2 moles of KClO3, or no, not KClO3, KMnO4, for every 5 moles of Cl2. And then the molar mass of KMnO4, I'm going just to look up because I want to save some time. KMnO4, potassium permanganate, 158.03. 158.03 grams of KMnO4 per mole. So the unit should work out. .81 divided by 24.5, oops, 24.8, 24.8 times 2 divided by 5 times 158.03, 25.00. 25.00 grams came in a 4. Are required to produce that much chlorine at this temperature and pressure. Okay, they're going to get a different amount. Because they're measuring an STP. You got 27.3. They're going to get more because it's same volume, but it's colder. Therefore, there's going to be more to it than that. 32. 32 is the old STP. This is the old 0 degrees C, 1 atmosphere. Old STP. I'm going to skip 32. This can happen though. What can happen is, the temperature is elevated. And so we're a little higher pressure than normal, and the temperature is going to elevate it at 214 degrees C. So one source of sulfur dioxide used in making sulfuric acid comes from sulfide ores by the reaction FeS2 solid plus 11 O2s yields Fe2O3 plus 8 SO2. Iron disulfide. So sometimes this is called iron disulfide. The reason it's called iron disulfide is because it's a weird species. Normally sulfide is what charge? -2. So if sulfide's -2, then what would that make iron? +4. Is iron +4 very common? No. No, it's not. And so it's not 2 sulfides. You know what that is? It's iron with an S2 2-. This is like peroxide, but it's not peroxide. This is equivalent, the sulfur equivalent to peroxide, but it's a heck of a lot more stable. This is called the disulfide ion. And it's an S2S with a 2- charge. That means iron is +2. This is actually iron 2 disulfide, or just iron disulfide, otherwise known as, does anybody know the mineral name for that? Iron disulfide is, looks like this. You might recognize it from the images. Let me see the images.
Pyrite?
Yeah, pyrite. Pyrite, also known as fool's gold. Yeah. Best image there. Let me see. Better image. There aren't many pictures of fool's gold. Probably because I'm calling it FeS2. Oh, no wonder my spelling. FeS2. There's some images. You can tell, this doesn't look like a. Look at the crystals. This That's one easy way to tell. You got the crystal shapes like this. Definitely different from the crystal gold. But anyway, we're out of time, so we're going to end with this.